In this lecture, we are going to see the importance of mass transfer. So you are going to study this topic in detail in CG4017 Bioprocess Engineering 2. But for this module, all I'm going to show is some basics. Yeah? So we're not going to go into the technical details or into the engineering ideas behind some of the kinetic expressions that I'm going to show in this lecture. Yeah? So all we are going to see is what's mass transfer and why it's so important when you think about a fermentation process. Yeah? So so before going to this topic, I just want to talk what is something called diffusion. So you should know the basics of diffusion. So imagine if you have two compartments, so let's separate it by some wall, and here you have solution, say a salt solution, and this side you have just pure water. Yeah? So once you remove this barrier away, if you take the barrier out, so the salt will move from this zone to this zone. Yeah? Just assume there is no mixing, so no mixing in in both of these compartments. So once you remove this barrier, salt likes to move from high concentration zone to low concentration zone. So, and the process which makes the salt to move from this left compartment to the right compartment, or if you want, you can call it as a high concentration zone to low concentration zone, we call it as diffusion. So so for this process to happen, like if you think there is some diffusion in a system, which means definitely you need some driving force, and that driving force is concentration gradient. So you need a concentration gradient. Yeah? So say C1 is your high concentration, C2 is your low concentration. The molecules will move from C1 to C2 until it reaches an equilibrium. Equilibrium point is a point at which if you put a probe in any of this compartment, it will read the same level, same concentration inside this box, if you want. And so that's the meaning of diffusion. So diffusion is a process where some mass in this case, so some concentration move from high concentration zone to low concentration zone, and concentration is nothing but mass per unit volume. So if you want, you can say like some mass is moving from one spot to another spot. In this case, it's some salt which is dissolved in the solution. So this is the principle of diffusion. And also one more thing you should remember is like so diffusion is more like a one step. It's a one step process. So it can go from high concentration zone to low concentration zone. So there is no way coming back. So if you have a reactor, if you have this high concentration zone somewhere at this part, say 0.1, and you have some low concentration zone, say 0.2, it can move from here to here. So there is no way it can come back. So diffusion is also one-way process, and it always go from high concentration zone to low concentration zone. So these are the principles of diffusion. And if you come back to your module bioprocess engineering, you know that many microorganisms can survive even in the absence of oxygen, but many of the microorganisms which they use in industries, they are called obligate aerobes. They classify under this category, which means they cannot survive if you cut the oxygen. So if you have a reactor, you need to supply O2 oxygen gas. If these microorganisms inside the reactor is aerobic microorganisms, so they call this as obligate aerobes, which means they cannot survive in absence of oxygen. So oxygen is a must. So that's the meaning of this. And 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 one more thing you have to remember about oxygen. Oxygen gas has a very low solubility, in water. So it has a solubility of roughly around 7.7 milligrams per liter at 30 degrees centigrade at room temperature, or sorry, at atmospheric pressure, say 1 atmosphere. So 7.7 milligram is really negligible quantity, yeah. So which means the the gas solubility is very low. So so imagine if you have a bioreactor, like say you have a nice mixing unit, even if you supply oxygen, it can if you have water filled into the reactor, it can take only 7.7 milligram per liter, no matter, irrespective of your flow rate, yeah. You can pump at a very high flow rate of oxygen into the reactor, but still you cannot dissolve more than 7.7 milligrams per liter. So that's the solubility limit, yeah? So your water cannot take, or you cannot dissolve more than this amount of oxygen in 1 liter of your water. And just imagine, in case if your, this is for pure water, if your water contains carbohydrates, like for example glucose, which is the essential nutrient for many of the microorganisms, or mineral salts, this value is going to go even less than that. So your solubility will be even less than 7.7 milligrams per liter. So the real issue here is not this. Okay, one issue is the very low solubility of oxygen in the water, and another issue is like, imagine you start an experiment. You, let's use the same reactor which I drawn here, and you have very low concentration, very low cell concentration inside, and you supply a lot of oxygen. So which means you the oxygen concentration should be more than enough for the cells to breathe, to respire, and then they can multiply. Yeah? So so that they can convert your reactants into products. But imagine after some time, once your reactor, inside the reactor, the number of cell concentration is going to replicate. It's going to replicate and fill the reactor, which means at this stage, the all of these microorganisms, they are going to breathe oxygen, which means they're going to take all the oxygen from the solution, which is dissolved in the solution. So which means you have to supply more and more oxygen, yeah. So as I said, you have only 7.7 milligrams per liter. That's the maximum you can dissolve in the water. So which means, and if your cell concentration exceeds some amount, they can take all this 7.7 milligrams per liter of water, sorry, 7.7 milligrams of oxygen per liter in the water. How to say, like, so it takes less than exactly 1 minute, yeah, like, it takes less than 1 minute to consume all the dissolved oxygen, dissolved O2 in the fermentation broth, or water if you want, you can call it. So what we need to do is like, you need to transfer oxygen so fast into that, into the reactor. So even if the cells are growing at a very much faster rate, and even if the number of cell concentration is 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 really high enough to consume all the oxygen which is dissolved in the solution, you have to replenish the water with new oxygen, you know. So which means you have to transfer more amount of oxygen into the water, yeah? So so this is the part where mass transfer becomes really important. Take a reactor. If you're just imagine you are bubbling some O2 bubbles, and you have your liquid here. For the moment, let it be water. So what you need to do is like, you have to move your oxygen from the bubble to the water. So this is something you have to know. So so and also how fast you move this oxygen from your bubble to liquid. Or in other words, what you are doing is you are dissolving oxygen from the gas bubble into the liquid. So which means you have to move. Just imagine this is a bubble. This have so many oxygen molecules. All these are O2 molecules. So you have to move these O2 molecules. You have to through this small gas film that makes the bubble, or that separates your gas from the liquid in the reactor. So you have to transfer these oxygen molecules into the liquid, so that which means you can dissolve the oxygen from the bubble to the liquid. So so at this part, O2 transfer becomes very important. So this is the for this module. We don't have to go into the full details. I can give you some. For I'm just going to say why mass transfer is important. And mass, whenever I talk about mass transfer, what I mean is like, imagine you have a gas bubble, you have some mass of oxygen, you are transferring some mass of oxygen from the bubble into the liquid which is inside your fermenter. Yeah? Just assume this is a reactor bubble, and you are trying to push your your oxygen mass from the bubble, or which is in the gas phase, to the liquid phase. So you are going to dissolve oxygen in the liquid. And normally, like if you take a normal reaction, how fast your reaction proceeds, that we can get some idea about this value or this quantity from the reaction rate. But when you talk in terms of diffusion is like you move your molecule from high concentration spot to low concentration spot. Yeah, C2, C1. This is high concentration and low concentration. So there is no chemical reaction. What's happening is just you are moving a mass from one spot to another spot via a process called diffusion. And diffusion happens just because you have a concentration gradient that allows you to naturally push your molecules, oxygen molecules, from the gas phase to the liquid phase. So so you need some expression to measure how fast you can move your oxygen. Or or if imagine you take a reactor and just just assume you have your water, and then you have some gas supply unit. Yep. So if you are supplying oxygen, so it's going to get dissolved eventually into the water. Yeah? So if you want to know how fast you are dissolving, or if just imagine you can measure that by adding a probe. Let's call this oxygen probe. So that will allows you to measure the concentration of oxygen. So let's call C is the concentration of oxygen. So how this concentration of oxygen is going to change with respect to time? Change in concentration with respect to time will be proportional to the concentration gradient. So as I talked about the solubility, as I said, like your solubility is like 7.7 milligrams per liter, say for example. Let's call this one as solubility of oxygen. Say we express them in milligrams per liter. So if you want, we can give some parameter, say C star. C star refers to solubility of your oxygen. And say at any time your concentration of your oxygen is C. Let C be the concentration of oxygen in the liquid at any time. Then your change in concentration at with respect to time will be proportional to this particular, the difference between your solubility and C. You cannot write this expression like change in concentration is proportional to concentration. This is a first order expression. But you cannot write this for the for for this type of problem, because you need a concentration gradient, yeah, not a concentration alone. You need a concentration gradient for diffusion to happen. And imagine, like, when your concentration reaches, when your C reaches C star, so the change in concentration will be equal to 0. So which means no mass will be transferred from your bubble to liquid. So see, I'm, I'm giving this expression without explaining any theory, because for this module it's not really necessary. All you need to know is why there is a diffusion, what's meant by diffusion, and how you transfer oxygen from the bubble to the liquid, and like, and once you supply oxygen, your gas molecules which are trapped in the oxygen bubble, it's going to diffuse into the liquid. And why that happens? Because you need a, because there is a concentration gradient. If there is no concentration gradient, there will be no transfer of mass of your oxygen from the liquid, from the gas bubble to the liquid zone. That's the basic thing you have to remember. So that's why you need a concentration gradient. So the change in concentration with respect to time, that will be proportional to the concentration gradient. And 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 in this case, your C will be less than C star. So this is a must condition. So why we need this expression? We need this expression to calculate how fast you are transferring the oxygen from the gas bubble to the liquid side. So dC by dt is proportional to C star minus C. For this particular case, if you remove the proportionality constant, will be equal to KLA C star minus C. So what is this KL? So KL is like how fast is something like how fast the oxygen molecules diffuse. So you have a bubble. Say this is your oxygen molecule. How fast they diffuse from here to the liquid part. Normally we express in terms of meters per second. This is like velocity. How many meters it transfers per unit time. So how fast your oxygen molecules move from the gas side to the liquid side. So the KL value measures this part. And what is this A? A is like, imagine if you have a reactor, you have you're spudging with oxygen gas so that the microorganisms can take the oxygen and survive. Imagine you have so many bubbles inside. So if, imagine this is your bubble, you have your oxygen molecules inside. It has to pass through this small area which is here. So you have to pass through the area of the bubble. So we can call this as interfacial area. Imagine if you have so many tiny bubbles, which means you have more interfacial surface area than one large bubble. So, and imagine if you have a reactor, you have so many bubbles inside, and you just calculate the total interfacial area of each bubbles, and just assume somehow we managed to calculate the area of all the bubbles, and let's call it A. And you know the volume of your reactor, how many liters of liquid you added inside the, how many, like how many liters of liquid you have inside the fermenter, say, and let's call you have V liters. So A by V, so that will be equal to your A. So what A is like, interfacial area of the bubbles, of the gas bubbles. volume of reactor. So whenever I say volume of reactor, it doesn't mean the whole volume, like the dimension of the reactor. No, it's just the volume of the solution you have. If you have 2 liters of solution, volume of reactor is 2 liters. Yeah. So coming back to this problem, the same expressions are changing concentration is proportion is equal to KLA C star minus C. So you need this one single expressions to calculate how fast you are moving your oxygen from the gas side to the liquid side. And normally the mass transfer should be very high, so that if you have too many cells growing inside the reactor, which means they're going to consume immediately. Once the oxygen enters the reactor, it's going to get dissolved into the reactor, and then your microorganisms, they're going to uptake the oxygen straight away from the liquid, which means you are going to continuously lose some concentration of oxygen, because all the microorganisms inside the reactor are breathing. So which means you have to replace whatever the oxygen you lost by consumption via breathing by the microorganism. So that's why your mass transfer should be really high. And how to calculate that? And for that you need this one single expression. So KLA, and as I said, if you have a reactor, if you have so many bubbles, it's almost impossible task to calculate all the area of the bubbles. So which means you cannot calculate this total area, interfacial area, although you know this volume of your reactor, which means you cannot predict this A value. So that's why, so change in constant, so that's why you have these two values together. So normally the unit of KL is meters per second. So it explains how fast your oxygen is diffusing from high concentration spot, which is your bubble, to the low concentration spot, which is your liquid. And then A is meter squared. A is area by volume. Area unit is meter squared, volume is meter cube. So this will be equal to 1 by meter. So the unit of KLA will be equal to meters per second multiplied by 1 by meter get cancelled, it will be equal to 1 by second. So normally this value should be, if the value is high, which means the mass transfer rate is really high. So if you want, we can simplify this expression by you can integrate this based on the initial conditions. dc by dt equal to KLA C star minus C. So dc by C star minus C is equal to KLA into dt. T is equal to 0, t equal to t. When t is equal to t 0, c will be equal to 0 and c will be equal to c. So what, these are the initial experimental conditions. Say when time t equal to 0, concentration of oxygen in the liquid is equal to 0. And when time t equal to t, say concentration, just imagine you start your experiment with 0 concentration, 0 milligrams per liter of oxygen, and then you started to supply oxygen, then your concentration is going to increase. So let's say the concentration at any time is equal to C. So that's what I said. At any time t equal to C, T concentration will be equal to T. So you can, if we can integrate this one, it will be equal to ln of C star minus C equal to KLA multiplied by T. This is a very simple first order type expression. So normally how to calculate this KLA value? So normally we do is like ln of C star by C star minus C. We take that in the y-axis and then you plot it against time in the x-axis. You will get some point like that. So it should pass through origin 0, 0, and whatever the slope you get, that will give some number that reflects how fast your 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 oxygen is transferring from the gas bubble to the liquid phase via those interfacial area available per unit volume. So the scale value should be really high, yeah. And how they how how they get this value in the lab. So in the lab, what they do is like they take a reactor and then they fill with a fermentation broth, or normally they use a water as like for example, and they just want to know how much oxygen they need to to supply, yeah, like, or how to achieve the conditions at which the mass transfer rate will be maximum. So they put an impeller and they will start to agitate, say like 400 rpm. So why do we put impeller? Is like once you put oxygen, if we add impeller, it will help to dissolve the gas bubble inside that reactor, which means the bubble will reside inside more time, and it also help to 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 move the oxygen molecules from the gas bubble to the liquid side. So anyway, we will study this in detail in CG4017. If you want, I already taught this one for the students, final year chemical engineering students. If you want, I can put the link like in the description box. So that will, if you want, you can go and watch the other two videos which I gave for the final year chemical engineering students. If you, in case if you are struggling to write about this topic, especially in the assignment, I recommend you to to look the two other videos that I posted, but for chemical engineering students, final year chemical engineering students, for the module CG4017. But for this module, all you need to know is importance of mass transfer and the usefulness of this one single expression which I wrote you here, this one. Yeah. So coming back to this experiment, so what we do in the lab is like we agitate at 400 rpm and then we supply air. Sorry, we supply nitrogen gas. So you all know air contains 0.21 mole percentage of oxygen, and the remaining mole percentage comes from nitrogen. Yeah. So once you supply pure nitrogen gas, what happens is like it knocks out all the oxygen. It takes 0.21 moles of oxygen, and then it comes out as air. So 0.79 moles of your nitrogen will react with 0.2 with 0.21 moles of oxygen, and then it comes out as air. And if you put a probe, just assume you have a nitrogen probe, sorry, oxygen probe, and if you plot here O2 concentration grams per liter and time, say, just imagine you start your experiment, say with say 7.7 milligrams per liter oxygen concentration. In the y-axis time, say minutes. In the x-axis, you start from 7.7 milligram per liter, and just assume this is the point you started your nitrogen supply. So as I said, nitrogen will knock out 0.21 moles of oxygen, and then it comes out as a air. So which means your oxygen concentration is going to deplete. Eventually it's going to reach near zero. So once it's reached zero, what we do is like we cut the nitrogen gas and then we pass oxygen gas, and then you just supply oxygen, and then your oxygen is going to increase, but it won't increase more than 7.7 because that's the solubility limit. You cannot dissolve more than that. Say you are performing this experiment at 30 degrees centigrade. So this is the solubility of oxygen in water. So what we do, so just draw a line and just assume this is time t is equal to 0, which means, and just assume these are your experimentally collected data. You have oxygen probe, and that allows you to measure your concentration. So which means you have something like time versus concentration, milligrams per liter, time in minute, say 0, 1, 2, 3, 4, 5, 6. And then you have your concentration starting from 0, say 1.2, 2.2, 3.3, 4.5. Eventually you reach 7.7, and then it will stop at 7.7. So because that's your solubility limit, you reached your solubility limit. So once you have this value, you go back to this expression, you plot ln of C star by C star minus C versus T. You will get something like that. It will be definitely a linear line, and it will pass through origin. It will pass through origin provided if you started your experiment with O2 concentration equal to 0 milligrams per liter. From this slope, you can get KLa. So you repeat one more experiment. This time you start your experiment from 500 rpm, and then you do one more experiment, say 600 rpm, say 800 rpm, and then you repeat, yeah, and then say this is for 400. You will, if you do the same experiment and if you plot, you will get something like 500, 600, 800. Then this one will give you some idea about at what agitation speed the mass transfer is maximum. So if KLa is high, which means faster transfer of oxygen to water. So that's how we get the data, yeah? Like if we know the reactor volume, and if we want to calculate the mass transfer coefficient, so all we need to know is like how to perform this experiment, how to get some value between time versus concentration. That will allow you to get some information about in that volume of reactor how fast you can transfer oxygen at some agitation speed, or in case if your live cells are breathing more faster, then which means you have to increase your, probably you can increase your agitation speed, or you can increase your oxygen flow rate, and then you can calculate again the mass transfer coefficient. So that's how it works. So these are the importance of mass transfer. So whenever we talk about mass transfer in bioprocess engineering, it corresponds only to the transfer of oxygen from the gas bubble to your bulk liquid. So the mass transfer of the mass transfer of oxygen becomes more and more important, especially when the concentration of your cells inside the reactor is really high. Yeah? So when if the concentration of cell is less inside the reactor, then 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 the whole process is not limited by the concentration of oxygen, because you have more than enough oxygen dissolved in the water for those very few concentration of cells inside the reactor. But once the cells start to multiply, I think this oxygen concentration plays a big role, and that's the time you have to worry about how fast you are transferring your oxygen from the gas to the liquid side. So I think I fairly covered this topic for this particular module. And by the way, one I forgot to mention, like the I said how we do the experiment in the lab, like you pass the nitrogen gas, it knocks out the some moles of your oxygen, and then it goes out as air, and then you supply pure oxygen, collect the experimental data, and then you calculate the mass transfer coefficient. So this is the, and this method of determining KLa, like using nitrogen gas to cut all the, to make your oxygen concentration 0 in the liquid, and then you supply with fresh oxygen. So or we call this method as a static method. Instead of oxygen, you can even supply air. Yeah, instead of supplying O2 gas here, you can supply air. Air itself contains oxygen, so that will also eventually increase your oxygen concentration in the water. So I think this is enough for this module. And probably if I ask you, if I give you some data like time versus concentration, and then if I ask you to calculate the mass transfer coefficient, or just the value of KLa, you should be able to calculate. You should know, all you need is to take this value ln of c star divided by c star minus c versus time. You have to plot your data here, and then you take the slope. That slope will be equal to KLA. I don't think we need to do solve some problem. This one, I think you can do it by yourself. Yeah, if you have time, if you have concentration, all you need to do is like ln of c star versus time. So you make a plot, then you take a slope, and from that you can get your KLA value. Yeah, so I think that's enough for this one. And then I'm going to upload this one in YouTube. Plus I'm going to upload, not upload, I'm going to send you the two more links that which I so those are my lectures for the other module, bioprocess engineering 2. But since I gave you some assignment, and some of you who do not have engineering background, they want to know a bit more detail about this mass transfer, I recommend you to watch both of those videos. Yeah, so there I also explained. Here I just showed this one simple equation here. Yeah? So this equation, it comes from a theory developed by Whitman. We call it as a two-film theory. If you go to that lecture, you will you you will have some idea about how to get this expression in a more theoretical fashion. Yeah? So this one I just explained to you in a more empirical way. Like you have a reactor, or if you have a fermenter, and you have some aerobic bacteria inside, and they need to breathe. Then so for that you need oxygen. Without oxygen they're not going to survive, because all of them are aerobic bacteria. And then where they are going to take the oxygen, so the oxygen comes from the liquid, which means you have to dissolve oxygen in the liquid. For that you have to supply some oxygen gas. Obviously you can supply as bubbles. Yeah? So you supply gas, so the oxygen bubbles enter the reactor, and you have to push the molecules from the bubble to the liquid, and that happens naturally because you have some um, because you have some concentration gradient. But as I said, you can dissolve only 7.7 milligrams per liter, which means the concentration gradient is also not a big number. Yeah, even if you start from zero oxygen concentration, the maximum solubility is only 7.7 milligrams per liter. So if you take the difference, 0 minus 7.7, that's equal to 7.7 milligrams per liter. So the concentration gradient is very low, which means the driving force for the oxygen to transfer from the bubble to liquid is very low. So that's why normally we add an agitation unit. We increase the gas supply into the reactor, which means you can pass more gas per unit volume of reactor. So that's why they increase the flow rate of air which goes into the reactor, just to speed up the transfer of O2, mm, O2 from the gas phase to the liquid phase. So these are the basic things you should remember. Yeah, so I think I can stop the lecture now. And uh, and and, and you I recommend you to watch those two videos. Don't skip those two videos. I'm going to put all the links for this one which I'm talking now, and also two more links which I designed for final year chemical engineering students. So try to watch all the three videos. You will get some idea. But for the exam, for this module, the understanding that you get from this lecture which I'm recording now, that's more than enough. Yeah. So, but if you want to gain additional engineering level understanding on this expression which you are seeing in the screen at the moment, that one you need to watch those two videos. And anyway, I'm going to teach you next year when you come for the when you register for CG4017. That time we will go into the details. And then apart from this, I'm going to upload a history of bioprocess engineering. I'm going to record it directly on the PowerPoint, and then I will upload it in Sulis. And then I will also talk quickly about one more video. Sorry, one more lecture directly on the PowerPoint. For that, there is nothing to write. I'm going to talk about the different scales of bioreactors. Yeah, like 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 large scale, small scale, and medium scale, and what type of products they produce at different scale. Yeah, so these things I will cover it in directly on the PowerPoint slide. So I will upload everything by tomorrow evening, which is Monday, and then after that all we have is downstream processing, and then I'm going to solve a few problems in enzyme kinetics, and I will I will try to briefly cover enzyme immobilization techniques, and I think that's enough. Yeah, so I will try to finish by week 10. So you will have the remaining 2 weeks for to study, and week 12 you are going to write some exams. Yeah, so I think I covered. Yeah, I'm going to stop recording this video. Thanks for listening.